EDX Core Pure Sequences in Series 2 Induction. Using induction to prove results about divisibility. Can we show that the following expressions are divisible by 3, where m is a positive integer? So if we look at this first problem and expand the brackets, we get 3m squared minus 9m minus 2m plus 6 minus m. Now if we collect like terms, we'll see a bit more clarity as to what's happening. So if we got 3m squared minus 9 minus another 2 minus 1, that's minus 12m plus 6, and then if we take out 3 as a common factor, I would avoid dividing by 3. It's much clearer if you take out 3 as a common factor. 3 lots of m squared minus 4m plus 2. Now it's factorised. We don't need to worry about factorising the bracket anymore. We've factorised out the 3, therefore it's definitely divisible by 3. And in this second example, 9 to the power m plus 1 minus 3. Again, to prove it's divisible by 3, we need to just rewrite the algebra. So using my laws of indices, I'm going to rewrite the first term as 9 times 9 to the power m minus 3. And now I can take 3 out as a common factor again. 9 times 3 times 9 to the m minus 1. Again, not too worried about whether I can do any more algebra on the bracket. What's important is that we've factored out the 3, and therefore it's divisible by 3. Slightly more complicated problem here, where we're going to need proof by induction. So is 7 to the power 2n minus 1 plus 3 to the power 2n always divisible by 8 when n is a positive integer? So the process. Step 1, we need to check that it is true for the first value where n is 1. We need to show that if the conjecture is true for any individual number, in other words n equals k, then it would also be true for the next one, n equals k plus 1. And then the conclusion step, as the result is true for n equals 1, and if it is true for n equals k, it would also be true for n equals k plus 1, then it must be true for all integer values at least as big as 1 by mathematical induction. So the first step, is it true when n equals 1? So when n equals 1, 7 to the 2n minus 1 plus 3 to the 2n becomes 7 to the 2 times 1 minus 1 plus 3 to the 2 times 1, which is 2. So we're looking at 7 to the power 1 plus 3 squared, 7 plus 9, which is 16, and that is divisible by 8. So this is divisible by 8, and therefore the statement is true for n equals 1. So that's the first step in place. So step 2 now. Assuming that the statement is true for n equals k, then 7 to the power 2k minus 1 plus 3 to the power 2k can be written as 8 times p, where p is some positive integer. So assuming it's true for n equals k, we can write the expression as a multiple of 8, 8 times p. So that's our assumption. Now we need to consider the next term, n equals k plus 1. So now we've got to show that 7 to the power 2 bracket k plus 1 minus 1 plus 3 to the power 2 bracket k plus 1 would also be divisible by 8. And the thing to remember here, two important points to remember. We can use this assumption statement whenever we think it's appropriate in our algebra, and our target is to prove that this term is divisible by 8. So let's start off with our k plus 1th expression. So just writing this out carefully. So this is the thing we're trying to prove is divisible by 8. So the first thing we can do is tidy up those indices. So this first one is 2k plus 2 take away 1, so that's to the 2k plus 1. And this one, expanding the bracket, is 3 to the 2k plus 2. Then we need to rewrite these terms. So the first one, I'm going to rewrite it, and I'm going to use, shortly, I'm going to use this 7 to the 2k minus 1. So I'd like this index here to be 2k minus 1, and I can do that by writing this as 7 squared times 7 to the 2k minus 1. Plus, for this term, I'm going to pull out a 3 squared, using my laws of indices. I'm going to write this one as 3 squared times 3 to the 2k. So we've got 7 sevens are 49, and this is the really important bit now. Now I've got this 7 to the 2k minus 1, that's where I'm going to use my assumption step. So I'm going to now replace 7 to the 2k minus 1 with 8p minus 3 to the 2k. So that's where I've used my assumption step there. Plus, tidying up the next term, I'm going to write that as 9 times 3 to the 2k. So if we expand the bracket now, we've got 49 times 8p minus 49 lots of 3 to the 2k plus 9 lots of 3 to the 2k. And just tidying that up now, we've got 49 times 8 to the p. We've got minus 49 lots of 3 to the 2k. We're adding on 9 lots of 3 to the 2k, so that's minus 40 lots of 3 to the 2k. And just to clarify the results even more, I'm now in a position to take out 8 as a common factor. So that's 8 times 49p minus 5 times 3 to the 2k. And you can see how we factored out the 8, and therefore this one would also be divisible by 8. So just the conclusion step now. So if the result is true for n equals k, then we've shown that it would also be true for n equals k plus 1. And as the result was true for n equals 1, it must be true for all integer values of n at least as big as 1 by mathematical induction. In the In the next session we'll be looking at using induction to prove results about series.